experiments, one of which is another Vegas-esque gambling experiment, and one is how we apply the Vegas-esque gambling experiment to our lives. For example, in this case, I brought life insurance, a life and disability insurance example. And you might ask yourself, how can you connect Vegas to that? To which you could say, you totally can, because everything is a roll of dice. I get in my boat, right into work, God knows what's going to happen. I can tell what usually happens. Usually don't get flats, I don't get hit. I don't get cold, I don't get frostbite, I don't fall down and hurt my shoulder. Usually. And then 4 weeks ago, I fell down and damaged my rotator cuff, first time in 20 years. It can happen. So the idea is, how do you measure that? You measure that with these tools that we're learning about. That's the whole beauty of it. You measure them with the tools we've learned about. But first Vegas. First Vegas. So I want to extend our discussion about dice. We talked last time about flipping one coin and figuring out on average how many times we have to flip a coin to get all the sides, or heads. I think it was heads all the time. Heads. We also talked about rolling one die and rolling two dice. We got those distributions. What I want to talk about now is an old game. This is experiment number 4, if you're keeping track. It's called Chuck-a-Luck. It's a pure game of chance. It's more popular in England than it is in America. It was more popular in America. It's kind of falling off. It's being replaced with craps now. And craps is awesome. Craps is totally awesome. I think I want to design a quiz for craps for you guys. Because craps is a very popular game. As I mentioned in other classes, everybody's like, yeah, I love playing that. And it's a fun game because it goes quickly. Very, very, very quickly. It's also extraordinarily goofy to understand the odds in craps. And the reason it's so goofy is because they want to take your money away from you. And they have to keep the... Anyway, we'll get to that in the quiz. So anyway, Chuck-a-Luck, here's the game in a nutshell. Number 1, you bet. That's called an ante. And let's keep it simple. Let's make it a $1 bet, just to keep it simple. There are payouts that are based on how much you bet, but let's just keep it simple at $1 for right now. We can extend it out to however much we need it to extend out to. So you walk up to the Chuck-a-Luck table, which I would show you if I had a network, but it's pretty simple actually. It's just this. It's usually on green felt like everything else in Vegas, with free drinks attached to it. And then it's broken up into 1, 2, 3, 4, 5, and 6. So you got this felt table, and you walk up with your $1 or a chip that's worth $1, where let's call it $1, and you pick one of the numbers to bet on. What number should we bet on? 4. I heard 2 4s and a 5. We'll go with 4. Put our $1 on 4. Okay. Now the game involves 3 dice, and they're in this thing called a bird cage, which is simply just, it's like a kind of like a wire hourglass that you spin. Spins around, spins around, spins around, spins around, and eventually comes to rest, and the dice fall on the ground. So you roll 3 dice. That's basically the idea now. You roll 3 dice, and you win. Actually, what do you think? How do you win? Based on what? Remember, you bet on 4. So, that's it. How many 4s you rolled? You rolled. You have to keep track of how many 4s you rolled. So we're gonna make a little laundry list here. So, how many 4s did you get? And you got to realize that we chose to bet on 4. It doesn't matter what number you bet on. 1, 2, 3, 4, 5, or 6. It's the same probability that we're going to be calculating as we go through. We just picked 4. So how many 4s could we get? You could get all 3, couldn't we? Now, you want that actually. You'll see why momentarily. What else could you get?
1, 4, 2.
1, 2. Don't forget, you might not get any. That's a possibility. And unfortunately, that's the possibility that costs you the most. Because if you don't get any 4s and you bet on 4s, you don't win anything.
So if you get 3 4s, you get $3?
Hold that thought. That's what Vegas controls. Thank you, Lauren. This is what we're going to do. We're becoming actuaries now. Actuaries set the premium payments for life insurance policies, and the actuaries in Vegas set how much you get and how much you lose based on the games. Thank you for that question. So now we have to answer that question very carefully. I'm going to put this in black. This is the actual first column of your distribution. So remember how your column has, your distributions have 2 columns. They've got a data column and a probability column. This is the first one, the data column. And Lauren's question is a good one. I'm going to call this the payout. do you think the payout is if you don't get any of the numbers you bet on?
0. Oh, you minus $1.
Good! It's negative $1 because you bet $1 to play and you don't get anything back. So you essentially lose your ante if you don't roll any of the numbers that you bet on. Very good catch on that one. Yeah, technically speaking, there's 0 payout because no money comes back to you. But remember, you put $1 in. Is that fair? You have to account for that loss of $1. You have to account for that loss of $1. Very nice. Okay, what if you get 1-4? Now this means exactly 1-4. So you could spin like 4-2-3 or 4-5-5. Then you can wish you bet on 5s. Or 4-5-6. 4-1-6, whatever. It would be very good, Austin. It would be a payout of 0 because the payout is a 1-to-1. I'm going to put that in orange next. You don't need to know this, but the payouts. Vegas often talks about payouts as a ratio. So this would be a 1-to-1 payout. For every $1 you bet, they're going to give you 1 back. Technically speaking, this would be a 0-to-1 payout up here. Because for every $1 you bet, they give you 0 back. So you'd subtract that minus that to figure out your expectation, if that makes sense. So 1-to-1 payout means you break even. You paid $1 to play, but they paid you $1 back, and then you're done. Cool? All right. What about 2? What do you think? That'd be a $1 because it's 2-to-1 payout. That's exactly right. This would be a positive $1 because it's a 2-to-1 payout. For every $1 you bet, they give you 2 back for every 1 that you bet. 2 minus 1 equals 1. How about 3? It's actually $9. It's a 10-to-1 payout on that one. Ah, yes. It's 9 because it's a 10-to-1 payout. And that, my friends, is what keeps people playing. That's what keeps them playing. They can adjust those numbers any way they want to keep people playing the game, and that's the beauty of it. And it's also the criminals. No, wrong word. Not criminal law. Mathematics. The genius of the mathematics. Evil genius of the mathematics. So, let me ask you a question. You walk into Vegas with a pocket full of $1 bills, and you're ready to gamble until they're gone. Alright? How long will it take? Let me rephrase the question. That's a stupid question because you don't have any bills yet. On average, when you go to play the game, how much money are you going to make? That's my next question. Yeah, on average. This is what we have to talk about, right? Because you can't talk about walking in with $1 and putting $1 down. And on average, what is that going to be? Because you're either going to lose it, get back 1, get back 2, or get back 10. So that's, but on average, if you play the game over and over again, what's going to happen on average, do you think? What's going to happen on average? But Austin has a vote, you're going to lose. I guarantee you that. Because there's a reason this game is in Vegas. It's because you lose on average. But my question is, how much do you lose?
Well, you have 3 dice.
You have 3 dice? Where are we going with this, Lauren? Where are we going with this?
Well, kind of like what we did yesterday, you have a 1 in 36 chance when you do like the 2, so then you have a 1 in whatever that 6 times 3 is. 6 times 6 times 6.
Oh, Caitlin. So 6 times 6 times 6. Does that make us? Okay, let's try to make this a little more formal. I love what you guys are saying. So first of all, let's get the sample space for the experiment. If you throw 3 dice, how many different possibilities can be laying there after you've thrown them? 216. Now, you call what Caitlin said. She said 6 times 6 times 6, and she tagged that off of what Lauren said about yesterday with the 2 dice was 6 times 6. Fair? So this would be 6 cubed, and the reason for that is you're throwing 3 dice. Each one has 6 possibilities. This is with replacement because you can get the same number on all 3 dice, or more than 1 die. So you've got a sample space of 216. Very nice. That's huge, because that tells us what there's a column we're missing, isn't there? If I asked you to average these 4 numbers, you would say, no, I can't. Well, you actually can.
You need your PMS.
But it would be wrong. You need the probabilities, because otherwise you're saying that losing $1 is the same as gaining 0 is the same as gaining 1 is the same as gaining 9. That's not true. Which one's the most common? Probably that. Which one's the next most common? Which one's the next most common? And then this one. The question is, how common are they? That's where Lauren's P of X column comes in. Beautiful. We're halfway, well, we're about a third of the way there, because we know the bottom of each of those fractions is 216, don't we? We know that each of these is out of 216. Out of 216. out of 216.
Which is a really low chance.
Good. How low is really low? Again, my question.
Not very good.
That you got to remember, the actuaries in Vegas need to know these numbers because they need to know how much to pay out so they don't hemorrhage too much money back. You'll see what happens when they do. I've got a great example from New York State in '06 where that actually happened and a couple kids were smart enough to catch it. Totally rad. Totally rad. So now let's figure out what the numerators are for each of these bad boys. And remember, don't forget, at the end of the day, what do these all have to add up to? Yes. Good. So pick one and tell me what it should be. Your call. I like where Laura was going with 2 dice. I think we can apply that very nicely, can't we?
1 and 2 are actually both 3 out of 216, right?
Say that again. Nathan.
Rolling 1 and a 2 are both 3 out of 216.
How come?
Because there's 3 different ways to roll 1, and there's 2 different ways to roll 2.
You've got the hardest part of it locked down right there. But it's actually bigger than 3 out of 216. Can I pause you for a couple minutes on that one? I want to come back to what you just said. What you just said, you've got the hardest part of this distribution you just figured out. But there's another part that we have to talk about too. But I think that will become more clear if we hit either 0 or 3 first. If you don't mind. Lauren, go.
Also, if you roll your 3 dice
Yes. And you're betting on what?
on
4.
4,
Mm-hmm.
how many other numbers? Let's see. Everything but 4. You would roll everything but a 4.
Okay, so you're going to this.
Yeah.
You're going to, so Lauren's going right to this.
How many
What's the chance we totally lose everything in this game and roll no 4s at all? Let me come back to that. Let's go straight to this one. You want this to happen, don't you? Let's not be negative. Let's be positive. We want this to happen, yeah? So how many ways can you roll 3 dice and have them all be 4? 1. They all have to be 4. This is Snake Eyes. But it's Snake Eyes on 3 dice. There's only, imagine and I wish if the network wasn't down, I have a simulation that actually shows you this.
Somebody just told me it was up in their classroom, but it's not up on my phone. So maybe you should try it.
Let me try it. Let me try it. That would be very, very good. I heard a so. Go with that so, Caitlin.
Well, I was thinking about the 0.
Hold that thought. I'm glad you're thinking about that 0. I want to make sure we're okay with the 1 out of 216. Let's see if this works.
Yeah, it's working.
1 out of 216. We got it good. Thank you, guys. So let's make sure we buy that first. There is one way to get all the dice to be 4. And you have to do it. You have to be 4, 4, and 4. That's it, the one way. Caitlin, tell me about 0.
Well, I was going to say, wouldn't you just go 5 times 5 times 5 because you have a 1 in 6. Like you're betting on 4, so there's 5 other possibilities.
She's using the last project. Good for you, sister. Check it out. Another way of looking at 1 and 216 is you have to roll a 4, and then you have to roll a 4, and then you have to roll a 4. What's the chance of rolling a 4? 1 in 6. Times 1 in 6 times 1 in 6 becomes 1 in 216. That's clever. Very, very good. I wasn't thinking of going that way. Thank you, Ruth. The same logic can be applied to here. If you don't want to roll any 4s, you have a 5-6 chance of not rolling any 4s on each of the 3 dice. So it's 5, 6, 5, 6, and 5, 6. So that together is going to be 125 out of 216. Thank you. Very nice. Very clever. Very clever. But I like what you did too. You broke it down to 5 times 5 times 5, which is the number of ways to roll the dice and not get any 4s whatsoever, because essentially you don't have 6 choices. You only have 5 choices for each die, because you can't get the 4s in there. Very good. Very good. So 125 out of 216, which is over 50%. That kind of sucks because we're losing money. And then 1 out of 216, we're making a lot of money. We're just not making a lot of money very often. So you got part of the answer right now. Yeah, you're going to bring back $9. Unfortunately, it's going to cost you $216 on average to win back 9. Okay, that's like buying every Powerball ticket to win the jackpot. Awesome. The problem is when you take taxes out and everything else, you end up losing money doing that. So don't do that scheme. Now, a question: how do we deal with this? So I want to break down the logic that just happened when we did this one here. What you guys did was you said, well, there's 1, 1, and 1. There's only one way to get 3 4s. Because you had either 4, a 4, and 4. And this one, Caitlin just broke us down. She went 5 and 5 and 5, yeah? To get to 125. Caitlin, go. Keep going.
So
I haven't forgot about you, Nathan. We'll get back to you back in this discussion, too.
I took 216 and I minus 126 since they all have to add up to
Okay.
100%. And then the $0 is a 1-to-1 ratio, and the $1 is a 2-to-1 ratio. But after I minused 126 from 216, I got 90, which would make it 30 for the $0 and 60 for the $1.
That is gorgeous. The only problem is that forces the payouts to match the probabilities, which is not guaranteed. I love what you just said. Did you get what she said? She took all the resulting that we have left. We have 125 plus 1 is 126. Take that away from the 216. We know there have to be 90 left split between those two, yes?
And we know the ratio.
And we know these ratios of payout. The thing is, these numbers in the X column don't necessarily have anything to do with these numbers in the P of X, but that's freaking clever. Yeah, but there's no marriage between them, unfortunately. But the fact that we know that we have 90 to play with is something. Because all we've got to do is get one of these, and we'll get the other one for free. Good! Now, can we get one of them directly? Nathan, talk to me about what you were talking about earlier.
Each rolling of 1 or 2 of the 4s.
Pick one. Which one do you want to do, brother?
Just do 1.
Just do one. Okay, beautiful. So here's my 3 dice, yes?
Yeah.
How many choices do I have for this?
6.
Well, do
You
I?
only have 1.
Well, it depends, doesn't it? What is that going to be?
Well, you want it to be 4.
I want that to be a 4. Okay, let's start with that. I want that to be a 4. What does this have to be?
Anything on paper.
Anything else but a 4, yes? Not a 4, and not a 4.
Which is, so these are going to be different numbers multiplied by each other because.
It's still 1s and 5s, but they're in
it's
different
gonna be
places.
1, 5.
Yes! So, that's a 1. You only have one choice. If you want that to be a 4, there's only one choice for that 4, yes?
That's a 5 and a 5.
And these, Sarah, are 5s and 5s.
Yeah,
Is that fair? You see what I just did there, friends? Actually, Nathan did it. I'm just kind of right now what he's saying. Now, logically speaking, you know what I'm going to do? I'm going to take that away and I want to look at this one as well. I lied. I said we're going to do one, not the other. We'll do both. So we got 1 and 2, yes? So now, looking at this one, where are the 4s? Where are the 4s?
Well, you're going to have 2 4s.
Where are they going to be?
1, 1.
So tell me where to put. Okay, so you're putting here. You're putting the 4 here, and the 4 here.
Well, it doesn't matter which way you put them.
Hold that thought. This is where it gets interesting. This is where it gets in. There's a reason I've been avoiding these until this moment. Your first couple projects had nothing to do with these. You were doing these distributions on your projects. I didn't tell you that because I didn't want to freak you out. But I was keeping you away from the middle zone. Here's why. So what's this going to be, 1s and 5s wise?
1, 1, 5.
That's 1, 1, 5. And we're multiplying those, yes?
Yeah.
We have to be. Now, 1 times 5 times 5 is 25, correct?
Yeah.
And the other one's just 5.
And that's just 5. That's a problem. That doesn't add up, does it? Why doesn't that add up? That logic seems flawless. Say that again.
Because you can get on the, say the ones that could be not a 4, or not a 4.
Remember what Nathan said earlier? He said something about a 3. There's 3 ways. What Austin just verbalized is that I asked you guys a bit of a loaded question. When we got to here, I said, where's the 4? And you said, Nathan, put it in the front. Nobody says it has to be that one. Couldn't it also be the second one?
But
And
you're
couldn't-
multiplying, so why does it matter where it goes?
Well, there's
Imagine the dice are 3 different colors. Good. Say it again, Austin.
There's 3 different ways to get the 1.
What? And
Oh, but you get 3 different dice.
You have 3 different dice. That's the thing. 3 dice are falling. Imagine, and I wish, if I knew the network was going to be down, oh, I logged in. Maybe we get the simulation after the break. Imagine the 3 dice in 3 different colors. Red, green, blue. This is forcing the red one to be a 4. Well, there is a 4 on the green one. Can't that one be a 4 as well? And if that one were a 4, not in this case, but isn't that a case where you can have 1 4? You might have it be 5 1 5. You might not have a red 4 and 2 non-red 4s. You might have a blue 4 and 2
But you're
non-blue.
still multiplying, so you get the same number.
Hold that thought, hold that thought. Hold that thought. And then what if the green one was the 4?
Oh.
You see, you're accounting for all the ways it can happen. We agree this is too small, yes? We're making it the right size. Now my question, and look, you're correct in that it's all multiplication, yes.
So that's a huge
Now careful, hang on. What goes here?
plus.
You add them.
Why is it added and not multiplied there? This is the culmination of your first 2 projects, FYI.
Oh.
I am not doubting that these are multiplied. Why are those added?
Because it's and or one of the
Oh!
numbers.
Oh my God, but that's the importance. Watch this, watch this. Say it with me. If you want, watch it, don't say it, there's gonna be a lot of words. Listen to me while I say it. If you want to get 1, 4, you've got 3 choices. You can either have the 4 on the first die, and not have a 4 on the second, and not have a 4 on the last one.
Yeah.
Or you could have a non-4 on the first one, and a 4 on the second one, and a non-4 on the third one. Or you could have 2 non-4s on the first 2. So Nathan, your 3 was 100% correct, but you can't ignore the other possibilities of the other dice rolling around. All the 3 does is places the 4 either here or here or here. Don't ignore the rest of the outcomes, the 1s and the 6s and the 5s and everything. So what did that end up being?
75.
75, yes. Now we already know if that's 75, back to Caitlin's awesome math from earlier, we know what this has to be.
Yeah.
This has to be 15. Do you see why it has to be 15 based on this argument now? There are 3 different ways to place the 2 4s. The first and second, sure, but it could also be the first and third, or the second and third. And there's your 3 ways, and oh, just put a 1 in front of it. So there you go. It's unfortunately in a 1 to 6, not a 1 to 3 ratio. But still, slick math on the beginning. You figured out what you had and what you needed. Very, very nice. Cool? Now what I'm hoping, fingers crossed, I can pull up my simulation and you can actually see these things arise. Let's take 5. I'll see if I can fire it up. I also want to get your guys' concerns on grades, because I know there were some point issues we want to chit-chat about. So why don't you meet me over the computer, take 5, get some air, get some water. I want to come back to this. This is the actuary's tool right here. That is the actuary's tool that they're going to use to figure these averages out. Thank you for helping me derive it.